Okay, welcome to free fall. Free fall is still acceleration. It is just a very specific kind of acceleration related to gravity. All right? So gravity is acceleration. Learn that, remember that. Don't let it get confused with stuff later. Gravity is acceleration. The scientifically accepted value, what people in, physics majors in college and things like that, what they use for gravity is 9.80 meters per second squared. However, to help you with math in this class, we will use 10 meters per second squared. We'll just round that to 10. It doesn't make too much of a difference because we're not working with such precise equipment that 9.8 and 10 make that big of a difference. And the math for you will be really easy because when you multiply by 10, you just add, you move the decimal to the right one. When you divide by 10, you move the decimal to the left one. Okay? But guidelines, just kind of rules to remember when dealing with free fall problems. Free fall problems have a tendency to look like there's not enough known information. Because a lot of times the free fall problem won't tell you gravity is 10 meters per second squared. It's going to assume you know that. Okay? But, so this sheet right here, this page, this is a list of things you want to make sure you know and remember. Alright? This page is very, very, very important. Okay? Write all of this down. Learn it. Alright? Most of this stuff makes common sense. So, we've talked about acceleration, positive being it's speeding you up, negative being it's slowing you down. Gravity can do both, depending on the situation. If you are falling, gravity makes you go faster. So, anytime the problem is referring to something that is falling, use positive 10 meters per second squared. Okay? Now, there can also be problems with gravity and free fall, where, say, you start by throwing something up in the air. When it's moving up, what's happening to the speed? Hopefully you are saying it slows down. So for a portion of a trip that is up, you have to use negative 10 meters per second squared. Okay? So a lot of free fall problems involve something going up and then coming back down. Alright? So the vertical speed at that very, very top highest point, when the ball reaches the very tip top, right before it starts dropping and speeding up again, its velocity is 0. Alright? For many free fall problems, that could be an initial or a final velocity, depending on the problem. Alright? Then part 3, if, say, you toss a ball from your hand and it leaves your hand with a velocity of 5 meters per second. Alright? If you catch the ball and your hand hasn't moved any, when you catch the ball, when it returns to the height that it left from, that's also going to be 5 meters per second. The only way to indicate the difference so that we know if you're talking about the beginning of the trip or the end of the trip is you have to indicate direction. You can do that by saying 5 meters per second up, 5 meters per second down, positive 5 meters, negative 5 meters. All right, just note that the direction or the sign does not need to be added until you're finally done doing calculations. Okay, so no matter what's going on, it would be plugged in as 5 meters per second. And the last thing is the time it takes for an object to reach its maximum height. So the time for this trip, this t, is equal to the time it takes for the object to fall back down to where it started from. So these two t's are equal to each other. Okay? So if I give you a problem and it says you toss a ball up in the air and it takes it 10 seconds for it to fall back down, if you want to know the maximum height, you want to know just 1/2 of it, so you have to divide that time by 2. Things like that. So this slide, really, really, really important, because these are things that will help you with free fall problems, because this stuff will not be given to you in the problem. It is assumed that since I have told you this, you know this. Okay? Another thing that is useful to talk about is the equations that are useful. You are used to these 4. Alright? These apply to free fall as well because gravity is an acceleration. These, however, are new. So make sure you get familiar with these. Remember, s equals distance. So if you want to know how tall something is, how far it falls, things like that, these are equations you want to use. Note, this is the full formula, all right? And you only need to use this if you have an initial velocity, okay? Many times, like say you drop an object off the roof of a building, when you drop the object, right before you drop it, what is the velocity of the object? 0, and that's your initial velocity. So more often, these become useful, all right? These two equations only work if your initial velocity is 0, all right? If you have an initial velocity, you have to use this one, all right? So if you have a VO, you must use the top equation. But if your initial velocity is 0, then your distance is equal to just 1/2 times at squared, okay? Or if you needed to solve for time, and the only time I'll ever make you solve for time is if your initial velocity is 0. But in free fall, solving for how long it takes something, like say you know the height of the building, it's 500 meters, how long is it going to take to reach the bottom? Then you would use this one, okay? Something else I want to note is the t squared. Only time is squared. The 1/2 and the a are not. So be very careful when you plug this into a calculator. Square the t separately, then multiply by a, then multiply by 1/2, just to prevent just not using your calculator correctly, okay? Whereas with the t equals square root of 2s over a, the 2s over a, all of that is underneath the square root sign. So figure out what 2 times s is, divide by a, then finally take the square root of that number, okay? So, and this equation, the t equals s over a, is coming from the equation above it. We're just rearranging to solve for t. So you start by multiplying by 2, which gives you 2s equals at squared, and then you divide by a, so you have t squared equals 2s over a, and then to get rid of the squared, you have to take the square root of both sides, which brings you back to that original equation, okay? So, become familiar with the equations on the right. So the next 4 slides are going to take you through some sample problems utilizing these equations. So, a rock dropped from a cliff falls for 25 seconds before hitting the ground. How high is the cliff? So, if you note, there's only one number given to you for this problem, yet you have enough to solve for it. All right? Because the rest of it is you should be able to tell from the problem and from those guidelines for free fall. All right, so what we do know for sure, t equals 25 seconds, and it is a rock dropping or falling, so that tells us that we're going to use positive 10 meters per second squared for our acceleration. And then there's also, if you're dropping a rock from the top of the cliff, what's the initial velocity? VO equals 0, and we want to know our distance. So the equation you're going to use is s equals 1/2 at squared. All right, so if we substitute in our knowns, s equals 1/2 times 10 times 25 squared, which ends up being 5. 1/2 times 10 is 5. And then 25 squared is 625. So 5 times 625, which gives you s equals 3,125. All right. So this is our second s, and our units are meters because we're solving for distance. Okay? So this is probably the most common problem you will deal with. All right, the initial velocity being 0, those are the most common problems I'm going to give you. Okay, so make sure you know how to replicate this one. This one's also in your assignment. Okay, or not this particular one, but something similar to it. So Here's an example with an initial velocity. At another cliff, you throw a rock with an initial velocity of 5 meters per second towards the ground. The rock reaches the ground in 25 seconds. How tall is the cliff? So, very, very similar to the last one, except this time we have an initial velocity. So, t is 25 seconds. Our acceleration is, again, positive 10 meters per second squared. This time, VO equals 5 meters per second, and S equals question. So this time the equation is S equals 5. Oh, sorry. That's not my equation. Equations are supposed to be variables. So S equals VO times T plus 1/2 AT squared. So if we substitute in our knowns, we're going to have S equals 5 times 25 plus 1/2 times 10 times 25 squared. Okay, which that looks a little bit more like 5 times 25 is 125 plus 10 times 625. I just made a mistake there. 1/2 times 10 is 5, just like the problem before. Okay, so it's going to be 3,125 plus 125. So our second S gives us 3,250, and our units, again, are meters. Okay, so the only difference here is that we can't drop off the VOT. We have to account for the fact that we already have a speed. So since we already have that speed, for the 25 seconds, we have at least that speed plus the increase due to the acceleration. Okay? If a ball is dropped from a 100-meter building, how long will it take to reach the ground? All right? So, again, it appears like we don't have a lot of information. We know S equals 100 meters. All right? Again, it's dropping, so our acceleration is going to be positive 10 meters per second squared. And it's dropping off of a building. We're not throwing it down with an initial velocity. So again, that's 0. And then our question is t. So this uses the other 0 initial velocity equation, that t equals the square root of 2s over a. So t equals 2 times 100 divided by 10, which that would be square root of 200 divided by 10, or the square root of 20. T equals, so the square root of 20 is 4.47. And our units would be seconds, because we're solving for time. Okay? And last one, something that is going upwards, all right? So, and this one's a tricky one, because there's actually two things we have to do. You throw a ball upwards with an initial velocity of 20 meters per second, all right? So we know, and our final answer is how high does the ball travel, all right? So we want to know a distance. We know that our VO equals 20 meters per second. Okay, we know that our acceleration, because we're throwing it upwards, we need to plug it in as a negative number, is 10 meters, negative 10 meters per second squared. Okay, now, let's think about this. We want to know this distance, so S equals question, and down here we have 20, and then we should also know that our VF equals 0 at the very, very top. VF equals 0. Initially, your gut reaction is going to be, oh, I want this one. S equals VOT plus 1/2 AT squared. Except, what don't we know? Hopefully you are telling me we don't know time, plus we don't know our distance. Okay? So eventually, yes, we will use that equation. But first, we have to find out time. And we have an initial velocity, a final velocity, and an acceleration. So the first equation we're actually going to use is this one. Time equals VF minus VO over A. Okay, so this is what we're going to do first. So let me finish that. S equals, so substituting in our knowns, we're going to have our final velocity 0 minus 20 over negative 10. So we get negative 20 over negative 10. The negatives cancel out. 20 divided by 10 is 2. And with units, t equals 2 seconds. Okay, so now we can add that up here. T equals 2 seconds. Now we actually have enough to use that equation. Okay, so let's finish that. So going with this equation, if we substitute in our knowns, we know our initial velocity is 20. We know it's going to take 2 seconds. All right, plus 1/2 times negative 10 times 2 squared. Okay, so that's going to be, this will give us 40, and then we're going to have negative 5 times plus negative 5 times 2 squared, which would be 4. So we'll have 40 minus 20, or once we get that down to 1, we get 20. And our unit, since we are solving for distance, is 20 meters. Okay? This is the trickiest they will get. Alright? But keep in mind, a lot of times, free fall, you might start with our basic acceleration equations to figure out time, and then plug that into the distance one. Okay? This is not an uncommon sort of problem. So bring any questions that you have to class, and make sure you remember to do the online form. See you in class.